Good morning, my dear friends. I hope you all are doing great, and so do I. So, my dear friends, we are here again with the chapter Biomolecules. In my previous class, I have spoken to you people about the cyclic structure of glucose. Correct? I told you that if we take on the open chain structure of glucose, this is what we have done in the previous class. You can have a look. When I took the open chain structure of glucose, what I did, the first carbon is basically here, aldehyde carbon, this one. So this is an aldehyde. And remember, aldehyde is always in this molecule. Aldehyde is a functional group. There are two functional groups in this molecule. One is CHO, aldehyde, and second one is OH. OH stands for alcohol. Between these two functional groups, the strong one is aldehyde. Correct? So highly reactive is aldehyde here. So we have aldehyde CHO. It's a functional group, and we can call it as it's a strong functional group here. So it's highly reactive. It's highly reactive. And this highly reactive functional group aldehyde, it interacts with the fifth carbon. You can have a look here. This fifth carbon is a last chiral carbon. So there is an interaction, there is a chemical reaction between the first carbon, which is the aldehyde, correct? And aldehyde is a functional group, it's a strong functional group, and the functional groups are highly reactive, correct? So the first carbon reacts with the fifth carbon. Fifth carbon is here, the last chiral carbon. Now you may have a question in your mind that why doesn't it react with the second carbon or third or fourth or fifth? It reacts with fifth, but why not second, third and fourth? You may be thinking like that. Because if it reacts with the second carbon, third or fourth carbon, what will happen? The ring size will be very small. The ring formation will be very small, and because of that small ring formation, you might have read about Bayer-Strain theory in first view. According to that particular theory, if the ring size is very small, if the cyclic structure is very small, made up of less number of carbon atoms, the force of repulsion between the bonds will be more. Due to more force of repulsion in a small ring size, the molecule is always unstable, correct? But when there is an interaction between the first carbon and the fifth carbon, the ring size will become almost, of 6 atoms, 5 will be carbon and 1 will be oxygen. You can have a look. So ring is 1, 2, 3, 4, 5 carbon atoms, and in that ring you have 1 oxygen. So this will be your ring containing 6 atoms, 5 carbon and 1 oxygen. So the ring size is bigger. So force of repulsion between the bonds will be very less. So molecule will be stable. That's why the first carbon, which is aldehyde here, it will interact with the fifth carbon to make a bigger ring. So repulsive forces will be less and the stability will be more. Now you have learned it in previous class. First carbon interacts with the fifth carbon. Then this is which structure? First of all, you have to tell me open chain structure of glucose molecule. And now you can see the equilibrium signs here. It can be converted into a cyclic structure, correct? But this kind of cyclic structure representation or this kind of cyclic structure representation is known as Fischer projection formulae. Fischer has represented these structures. I told you last time, the Fischer says us that a particular molecule can be represented how? In terms of the vertical lines and the horizontal lines. You can have a look here, here and here. You have a vertical and horizontal lines with you through which the glucose structure has been represented either in the open form or in the cyclic form. Remember, this is a cyclic form. In this cyclic form we have 5 carbon atoms and 1 oxygen. And the 6th carbon is outside the ring, correct? Here we have how many carbon atoms? 5 carbon atoms and 1 oxygen inside the ring. But outside the ring, you have 1 carbon atom. Remember, in case of glucose molecule, when open chain structure changes into the closed structure, in cyclic structure you will be finding out that you will have 5 carbon atoms in a ring and 1 oxygen. And 6th carbon will be outside. Correct? So now if you look at this molecule, it can change either into this form. I told you last time this is alpha form. Or it can be converted into which form? Beta form, depending on the position of OH group. Here the OH group on first carbon, I told you last time this first carbon is known as cyclic hemiacetal carbon. This is here also cyclic hemiacetal carbon. You can also call it as anomeric carbon, I told you last time, anomeric carbon. And that is carbon number 1. This guy is also which carbon? Your anomeric carbon. Anomeric carbon. And here carbon number 1. So position of OH group on right side of anomeric carbon. Right side of anomeric carbon is alpha. The position of OH group on left side of anomeric carbon is beta. Once again, the position of OH group on right side of anomeric carbon is alpha. Position of OH group on left side of anomeric carbon is beta form. Natural sugar. This is also a natural sugar. So it's a D form. Natural sugars are always capital D. And capital D also means, you look at this structure, 5th carbon has OH group on right side. Last chiral carbon has OH group on right side. So capital D and capital D. Experimentally it has been found, if you take the solution of this alpha form and the beta form solutions, this guy will rotate the light in clockwise direction and this guy is also rotating the light in clockwise direction. So plus and plus. Now let's come. This is a glucose molecule, this is a glucose molecule. Now look, these are Fischer projection formula for which thing? For cyclic structure of glucose. I hope you have understood this particular fact. I also told you something. What was that? Beta D glucose and alpha D glucose, they are called as anomers. Why they are called as anomers? Last time I told you. Because they differ in the position of OH group at the first carbon. That first carbon is anomeric carbon. So they differ in the arrangement of OH group at carbon number 1, which is also known as anomeric carbon or hemiacetal, cyclic hemiacetal carbon. My dear friends, these representations of molecules like open chain structure can either change into alpha or open chain structure can change into beta. Then from alpha form it can change back into open form. Then from open form it can change into the beta form. So try to understand this factor. Okay, so my dear friends, I hope you have understood. This was our previous topic. But now there's a point which I want to discuss. To represent, do you think that this is the perfect cyclic structure? Do you think that this is the perfect cyclic structure? No. These are not perfect cyclic structures represented by Fischer. So when these are not the perfect cyclic structures, okay, then there must be the perfect cyclic structures, correct? And the perfect cyclic structures, okay, were represented later by Haworth. So let us represent the cyclic structures of glucose, okay, in terms of Haworth structures. These are Fischer structures, this one, and this one. This is cyclic, this is also cyclic, but they are not well-defined cyclic structures. So in order to understand it in a well-defined way, let's go to the Haworth structure for glucose. The Haworth will represent this alpha form and beta form in the most perfect way through a different pattern of cyclic structures. So we'll go into that. Right? So my dear friends, the Fischer has given us the cyclic structures, okay, of a particular glucose molecule. He explained that how the open chain structure will be in equilibrium with the alpha D glucose and will be also in equilibrium with the beta D form, correct? But those were not the perfect designed structures for the cyclic structure of a glucose molecule. Correct? So there came one more person. His name is Howard. What does Howard say? He has explained the structures of glucose, the cyclic structures of glucose, in a much perfect way in comparison to Fisher projection formula. So let's understand. Look here, first of all, let's have a look at this structure. If you look here, this is our Fisher projection, the cyclic structure of glucose, and obviously it's a cyclic structure of glucose. Correct? Now, how many carbon atoms are here? 1, 2, 3, 4, 5. And 1 is oxygen. Don't consider this point, this and this point as carbon. They are nothing. Remember that thing. So 5 carbon atoms and 1 oxygen. This is our Fisher projection. It's our previous topic. Now, we are talking about Harville. He also represented the glucose in which form? He also represented glucose in cyclic form. So his cyclic structure, the Harville cyclic structure, was not based on these horizontal and vertical lines, which is actually the Fisher projection. Correct? It is based on this particular ring called as Pyron ring. What is Pyron ring? Look here. How many carbon atoms are in Pyron ring? 2, 3, 4 and 5 carbon atoms are here. Correct? So 1, 2, 3, 4 and 5. And 1 is oxygen. So Pyron ring. Remember one thing first of all. You will study it actually. If any cyclic structure contains a heteroatom. Heteroatom means different atom. These are 5 carbon atoms, but this is oxygen. So this oxygen is known as heteroatom. And carbon, 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 carbon. They are same. So homo. And this is hetero. So if any cyclic structure contains the heteroatom, it becomes heterocyclic compound. So understand this particular thing. So this guy is our heterocyclic compound. So which one is our heterocyclic compound? Pyron. Why? Reason? Reason is that it does not contain same kind of atoms, but it contains a different kind of atom as well, and that is oxygen, and it's a heteroatom. So it's a heterocyclic compound. Now if you look here, in this particular structure, it's a Pyron molecule. Correct? In Pyron structure, you will find out that it has 5 carbon atoms and 1 oxygen. So I will mention here, it contains 5 carbon atoms and 1 oxygen atom. These pi bonds are not necessary here. You can place this structure in absence of pi bonds as well. So now if we talk about Pyron, it contains 5 carbon atoms and 1 oxygen atom. And that oxygen atom is your heteroatom, and this compound is known as heterocyclic compound. So the Harvard structures are based on this Pyron molecule. He has designed the cyclic structure of glucose based on this Pyron molecule. So let's understand how. First of all, if you go back to this structure, which is a Fisher structure for glucose molecule, correct? Okay. Now, have a look here. How he has drawn the cyclic structure of glucose. Have a look. Let me take this ring. Okay. Let me turn it a little bit to the right. Okay. How many carbon atoms are here? 1, 2, 3, 4 and 5. So let me number it as 1, 2, 3, 4 and 5. Correct? How many are here in Fisher projection? 1, 2, 3, 4 and 5. Correct? First carbon is in connectivity with which carbon? Fifth carbon. Through which atom? A heteroatom. What is that? Oxygen. Please try to understand. The first carbon is in relationship with which carbon? Fifth carbon. Have a look. Through which atom? Oxygen atom. And that is Fisher projection. Same is the case here. The first carbon, have a look, first carbon is in connection with which carbon? Fifth carbon. Through which atom? Oxygen, hydrogen atom. So it's the same thing. But this representation is far better than that representation. And this is Harvard structure. Okay, let's understand further. If you look at the first carbon here in Fischer projection, I told you last time, it is a cyclic hemiacetal carbon. Cyclic hemiacetal carbon. You can also call it as anomeric carbon. And remember, which carbon is this? Carbon number 1. Correct? So now, my dear friends, who is this carbon number 1? Carbon number 1 is cyclic hemiacetal carbon. So this is cyclic hemiacetal carbon, also known as anomeric carbon. Correct? So this is your anomeric carbon. Now what is important here? You have to remember that. Important thing is that the position of OH group on first carbon. There are two groups on first carbon, OH and H. What is the position of OH group on first carbon? It's on right side. Which form is this? Alpha. In this structure, OH group on right side, try to understand, means in this structure it will be below. So OH group on this, in this compound on right side means in this structure it will be below. What is the OH group on the third carbon? Left side, and left side means above. So remember two terms here, my dear friends. Two terms you have to remember. Let's focus it here. Can we focus it here? Okay, cool. If you have, remember left means up. I am talking for OH group. For OH group, left means up. Okay, let me represent it here because it will not be much visible here. So let me talk about OH group. Correct? If here OH group is on right side, right. In this structure, right means actually below. In this structure, why is the OH group on third carbon? Left. And remember, left means here up. Try to understand that. Clear? So let's compare it. Here OH group is on which side? First carbon, right side. And here on first carbon, right side means what? Below. Okay? If OH group is on which side? On third carbon, left side. And left side means actually up. Remember that thing. Correct? Right side means below and left side means up. Let's have a look. First carbon has which group? H and OH. OH is which side? Which side is OH? Right side. Right side means below. That means I can place it like this. What is here? H. This is for OH group, okay? Now you can see. Why is the OH group? First carbon, OH group. Right side. What does right mean? Below. So it's below. Correct? Okay. Second carbon. What is the OH group on second carbon? Again the right side. Correct? Second carbon, OH group right side. So right side means what? Below. It will be below. What is the another thing? H. H will be here. I hope you are understanding my point. Correct? Third carbon. Look at third carbon. Where is OH group? On left side. What does it mean by left side? What do you mean by left side? Up. So OH group will be up and H will be down. Because third carbon OH group is left side. Left means up. So left means up. So OH group is up here. Correct? Fourth carbon. What is the OH group on fourth carbon? Which side? Right side. Right side means what? Below. Right side means below. So OH and H. Now let's talk about the fifth carbon. See here, the fifth carbon does not have OH group because that OH group has already reacted with first carbon. Correct? Now fifth carbon has H and what else? Fifth carbon has H and CH2OH. Sixth carbon is also attached to which carbon? There are two groups on fifth carbon. Fifth carbon is attached to hydrogen and sixth carbon, what is that? CH2OH. Now, H should be placed down. Because of steric hindrance, we have to put it like this. And CH2OH group, sixth carbon will be outside. So that is sixth carbon. Look at the fifth carbon here. This is your fifth carbon here. Fifth carbon has H and CH2OH. Write CH2OH up and H down. So don't apply this particular formula for this CH2OH. Keep it directly outside because sixth carbon is outside the ring. So this is the structure. And I have designed this structure from which formula? Fisher formula only. But this structure and this structure, this one is more perfect because it gives us more information about the stability of a particular molecule as compared to this molecule. Correct? Now have a look. Right side means low. Correct? So on first carbon OH group is on right side. And the first carbon OH group, first carbon means what? Cyclic hemiacetal carbon or anomeric carbon, and OH group is on right side. Right side means basically below. Then which form is this? This is your alpha form. With your permission, okay, I would like to write down its name and all, but before that, please make a note of this. Okay, then I will write down its name. What will be the name? But let me give you a little idea here. I am designing this structure from this, so it will be alpha. This is D form, this is the same D form, this is plus, that will be also plus, because it's exactly the same thing, but representation is different. This is Fisher projection and this is Harwood structure of a particular glucose molecule. And remember here, below means right and above or up means what? Left side, OH or left side, correct? So let's discuss about it. Correct. So my dear friends, let us see here. This first carbon is your which carbon? Cyclic hemiacetal carbon or anomeric carbon. What is the position of OH group? Down. Down means basically here below, or in this molecule it's on right side. So right means here below in this structure. So obviously this is also which form? Alpha form. So what is alpha form according to Harwood structure? It means the presence of OH group, okay, below, or we can say downside, or downwards, presence of OH group downwards on the anomeric carbon, that is first carbon, correct? So alpha form. Second thing, it's a natural sugar, so D form, positive because it can rotate the light in clockwise direction. And now I will mention one point here. For glucose, I will write down gluco. Gluco stands for glucose. Or glucose, you can say glucose. Correct? Now, this structure has been derived from this ring, and this ring is pyrrole. So, this structure contains how many carbon atoms inside? 1, 2, 3, 4, 5. This is outside, you leave it. 5 carbon atoms and 1 oxygen. 5 carbon atoms and 1 oxygen. So which ring is this? Pyrrole. So this is also a pyrrole ring. So I can call it as gluco. Gluco stands for glucose molecule. Then I will write down here pyrrole, because this structure has been derived from this particular structure. So it is pyrrole. And we know it's a sugar. And for sugar I will use a term OSE. It will give me sugar. So now my dear friends, what is the meaning of alpha here? Alpha means here position of OH group. You can say right or you can say below, both are same. Right in Fisher projection and below in which structure? In the Harwood structure. Correct? So position of OH group on right side or below in, come on, or we can say on C1. C1 means which carbon is that? Anomeric carbon. Once again I am telling you, right side in Fisher structure and below in which structure? Harwood structure. Both are same. So this form is known as alpha. We call it as alpha anomer. Alpha anomer. You can also call it as alpha anomer. Correct? D, no need to explain it much. D stands for the configuration, the position of OH group on right side of last chiral carbon. I have discussed it. All natural sugars are having capital D configuration. Plus means it can rotate the light in clockwise direction when you make a solution out of it. Glucose stands for this term gluco. Glucose stands for glucose. Pyron means a heterocyclic compound. I told you pyron is a heterocyclic compound. It contains how many carbon atoms? 5 carbon atoms plus 1 oxygen. So pyron, everybody knows about it. It's a heterocyclic compound. Heterocyclic compound. It contains 5 carbon atoms plus 1 oxygen. That's 1 oxygen, you can remember. It's 1 oxygen. And os is a suffix. I told you last time, os is nothing but it's a suffix. Let me mention it here. And what does it represent? Represents sugar. Represents sugar. So glucose is a sugar molecule. Let me put it a little down, this thing. Left. Okay, cool. Represents sugar. So meaning of os is, it's a suffix. It represents sugar molecule. Pyron is a heterocyclic compound. It contains 5 carbon atoms and 1 oxygen. Because 1 carbon is outside, you leave it. Inside you have only 5 carbon atoms and 1 oxygen. So it's a heterocyclic compound. Glucose stands for glucose molecule, sugar molecule. Plus means it can rotate the light in clockwise direction. D means in open chain structure, if you open up for this molecule, open chain structure, this is closed. But if you look at the open chain structure, the natural sugar will always have the OH group on the right side of last chiral carbon, that is 5th carbon. On the right side of last chiral carbon. So that is capital D. Alpha means the position of OH group. The position of OH group on right side or below. On which carbon? Cyclic hemiacetal carbon or anomeric carbon, which is the first carbon in glucose. I hope you have understood this particular term. This structure was for alpha D plus glucopyranose. Now I will easily draw it for beta D plus glucopyranose. I have to only change the position at which carbon? First carbon. That's it. I am not taking mirror image. Mirror image means if I change the position of groups at every carbon. If I change only at first carbon, it will become the beta form, which I told you in previous case. I hope you have understood this thing. So please make a note of this. Let's have a look at the beta form now. This is your Havel structure and this will be also your Havel structure. Exactly same, you can draw it with me now. Correct? This is your pyron ring, so it's pyron, correct? What is the position of OH group on first carbon? Okay, this OH group is basically below. Below basically means right, remember. I will only change the position of OH group on first carbon, which I was doing in Fischer's structure also. I was changing the position of OH group on first carbon and I was getting anomers. What are those anomers? Alpha and beta glucose, correct? Here also I will do the same thing. I will change the position of OH group on which carbon? First carbon, which is cyclic hemiacetal carbon. So I will change it. So where is the OH group on first carbon? Below. Below means what? Right. So I will put it up. And remember, up means basically what? Up means here, if you look at Fischer's structure, up means basically left. Correct? We have to change the position of OH group only at which carbon? First carbon. Other carbons, it will be same. Please and please remember, you have to change the position of OH group only at first carbon, which is cyclic hemiacetal carbon or anomeric carbon, C1. Other carbons, you have to keep the positions of groups same. No modification is required at other carbons. So rest of the structure is same, HOH. So no need of changing it. Please have a look here. H, OH, it will be same. Here OH, H. Here H, OH. Here will be H. and here will be CH2OH, which is 6th carbon. So first, second, third, fourth, fifth. And what is this first carbon all about? This first carbon is this carbon. What is that carbon? Cyclic hemiacetal carbon or anomeric carbon. So my dear friends, you are only changing the position of each carbon, first carbon. You are not changing the position of first carbon actually, you are changing the position of OH group on first carbon. Here it is down and here it is up. So down here stands for right side and up here stands for left side. So they are anomeric forms because they differ in the position of OH group at first carbon, which is anomeric carbon. So if this is alpha, this is, my dear guys, beta. Now you will think that it's a natural sugar, this guy is also a natural sugar, and for natural sugars, my dear friends, capital D. And if you open up their open structure, rather if you open up the cyclic structure, you will get an open structure and you will find out that OH group will be present on the right side of last chiral carbon, that is 5th carbon. So capital D, natural sugar. It has been experimentally found that it can rotate the light in clockwise direction, so plus. Now you may be thinking that why not minus? Remember, I am not taking the mirror image of this molecule. I am just changing the position at only carbon number 1. If I change the position of groups at every carbon, exactly opposite I will make. Here also I will change the position, 3rd carbon, 4th carbon, 5th carbon, everywhere if I change the positions of the groups and make them exactly opposite, then it will become a mirror image, then plus will become what? Minus. But I am not doing that. I am changing only the position of OH group at which carbon? First carbon. Only one position I am just altering. I am changing the position of groups at first carbon. So you can't write down from plus to minus. Plus to minus can be only possible when you are changing what? When you are making the structure exactly opposite at each carbon atom. Correct? But you are doing it at only one carbon atom. So it cannot be a mirror image. So optical activity is same. It's plus, it's also plus. This is also glucose. Glucose stands for glucose, a short term clipped word for it. Pyron means it also contains a 6-membered ring with 5 carbon atoms and 1 oxygen. This is outside, I leave it. And ose is a suffix used for sugars. So now we have 2 forms here. Alpha D glucose, alpha D plus glucopyranose and beta D plus glucopyranose. These are basically the Havel structures. They are cyclic structures of glucose by this particular person, Havel. Correct? So what are these two now? Exactly, they are anomers because they differ in the position of what? OH group at carbon number 1. So alpha D plus glucopyranose and beta D plus glucopyranose are anomers because they differ in the position of OH group at carbon number 1, which is cyclic hemiacetal carbon or anomeric carbon. I hope you have understood this particular point. So my dear friends, let's write down one important point here. That will be, if we talk about now Havel structures, you have 2. Havel structures. For which molecule you are doing it? For glucose molecule. Correct? And these are basically cyclic structures of glucose, we can say. Cyclic structures of glucose. So let's take it out. Now have a look. Please draw with me. You can easily get it because it's very much important. If you draw these 2 structures perfectly, then you can easily understand disaccharides, the glycosidic bond, then polysaccharides. You can do like this in a flash. But please and please remember these structures, correct? It's very important. Let me draw one more pyron ring. Let us suppose this guy is which form? This is alpha. And this guy is beta. Alpha means where will be the OH group? OH group will be down on first carbon. Beta means OH group will be up on first carbon. Correct? So here OH group is down and here OH group is up. This is alpha and this is beta. Correct? It's a natural sugar. So capital D, it will have a OH group. In open form, it will have a OH group on right side of last chiral carbon. This is also capital D. If you make a solution of this, it will rotate light in clockwise direction. So plus. If you make a solution of this, it will also rotate the light in clockwise direction. Which light? Plain polarizing light, which I already discussed. And you know, this is gluco. Gluco means glucose, a clipped word, short word for the glucose molecule. And this ring is basically pyrrole ring. So I'll call it as pyrrole. And we know it's a sugar, so we'll call it as OS. Correct? Same thing here. It will be gluco. For glucose, pyrrole means you have a 6-membered ring with 5 carbon atoms and 1 oxygen. And O stands for sugar. Correct? Let's do the rest of the thing is same. H, OH. Here also H, OH. Only first carbon will change. Position of OH group on first carbon will change. Correct? Third carbon same. OH, H. Come on, H, OH. Same here. No need to do much of the hard work. You just have to do the smart work here. First carbon only is changing. That's it. Then you have H and the 6th carbon we know it's outside. CH2OH. That's the 6th carbon. Put H here and the 6th carbon is outside. Only change is at first carbon. And you know, first carbon is nothing but anomeric carbon. This is your anomeric carbon. Correct? Now here, same thing. First carbon is anomeric carbon. So carbon number 1, carbon number 1. So these two molecules differ at the position of OH group. Okay? So I'll call them as, once again I am writing anomers here. What are anomers? Okay? Molecules which differ in position of OH group at anomeric carbon, that is C1 in glucose. Let me mention that in brackets C1 in glucose, because in fructose carbon number 2nd is anomeric carbon, but in glucose carbon number 1st is anomeric carbon, so you have to keep it in your mind. Molecules which differ in position of which group? OH group at anomeric carbon, that is carbon number 1 in glucose, are said to be anomers. So my dear friends, these two guys are nothing but they are anomers. So example will be example alpha D. I will directly write down alpha D glucose. No need to mention entire thing. And beta D glucose are anomers. They differ only in the position of OH group at first carbon. If you look at 2nd carbon, 3rd carbon, 4th carbon, 5th carbon, 1st, 2nd, 3rd, 4th, 5th, 6th, there is no change. Only first carbon is there, but there is a change. Now my dear friends, if we look here, because some of the people among you, I know the psychology of students, okay? Some of the people among you will be thinking that this is plus, this guy is also plus. But previous time we were telling that like plus and minus is only possible in case of mirror image. Have a look here. Let us suppose if I take a glucose molecule, okay, 3, 4, 5 and 6, CH2OH, OH, OH, 3rd carbon OH here, H, 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 and let's write down the OH and H. This is your glucose, correct? Let's suppose this is plus glucose, or we can say D plus glucose, correct? This is D plus glucose. If I take its mirror image, What will be its mirror image? Have a look. You may think we'll draw it like this. This way also you can draw, but no need to change at first carbon because it's just a functional group. You can mention also it like this. CHO, aldehyde, and here also CHO. Okay? See here. Right side and here is left side. First, second, third, fourth, fifth and sixth. Third carbon, OH group left side and here it will be right side. Right side, left side. Right side and here it will be left side. One, two, three, four, five, six. This is L. Because position of OH group is on right side on last chiral carbon and here it's on left side of last chiral carbon. So L, capital L. Position of OH group on right side of last chiral carbon, that is capital D. Position of OH group on left side of last chiral carbon, that is capital L. These two are mirror images of each other. So this is plus and this is exactly opposite. So this is minus. It can rotate like in anti-clockwise direction. And this is a glucose molecule. Now look here my dear friends, in these two structures, I told these two structures previous time if you remember, I call them as enantiomers. Please try to understand. Why? Because there is a difference in the arrangement of groups at every carbon, second carbon, third carbon, fourth, fifth, everywhere groups are exactly opposite. I am changing OH on right side, left side, left side, right side, right side, left side, right side, left side. Means I am changing the position of groups at every carbon, every chiral carbon. Yes? So, if this is dextro, this becomes levo. Correct? But look here my dear friends, in these two structures if you see HOH, HOH, OH, H, second, third, fourth, fifth. Second, third, fourth, fifth. There is no change. They are same. There is no change in the position of groups at second, third, fourth and fifth carbon. They are same. But there is only the change at carbon number 1. Yes? So through that particular change they become anomers. Correct? But their optical properties are same. If this is dextro, this guy is also dextro. Correct? But if you look there at these two structures, the position of OH group is changed at every carbon, second, third, fourth, fifth. They become exactly mirror images of each other. And when they become exactly opposite structures at every carbon, then what happens? Their optical activity also becomes from plus to minus, and I call them as enantiomers. But here the position of OH group changes only at carbon number 1. So I call it as what? Anomers. But their optical activity is same. Because these two are not the mirror images of each other. Okay? They are anomers. Thank you so much. In the next class, we'll be dealing with the cyclic structure of fructose molecule. Till that time, have a good day. Yo-yo.